this is a little more of an advanced example of doing rectangular and polar conversions. We have sort of this x squared plus y squared squared, and then there's this difference. So we're going to have to use that and some trigonometric identities to come up with something that's pretty meaningful. So let's sort of get to it and see what we can exploit. And what you're going to find is, I think graphing this in polar is actually going to be easier than graphing it in rectangular, but you know, everybody's different. So r squared equals x squared plus y squared. Whenever you see that, you should always exploit it. You should, if you plug in this just directly every time, you're going to have to end up reducing in a way that just takes extra time. So it's going to be r squared squared minus 6 r cosine theta squared minus r sine theta squared equals 0. So we plugged in for x and y, and then we plugged in here. So that makes our lives a little easier. So now we end up with r to the fourth minus 6 r squared cosine squared theta minus r squared sine squared theta equals 0. So then I can factor out an r squared. I get r to the fourth minus 6 r squared cosine squared theta minus sine squared theta, 0. Now, there's a trig identity I would love if you knew this trig identity, but you may not. So you can replace this whole thing with cosine of 2 theta. That's that double angle formula. But it's nice, right? So now I have this, which gives me r to the fourth equals 6r squared cosine 2 theta. And then I can divide both sides by r squared, getting me r squared equals 6 cosine 2 theta. So this also gets me that r is plus or minus the square root of 6 cosine 2 theta. Now, this is not a great representation. It's okay, but there are you have to watch out. Just make sure that you watch out for your domains here. Obviously, anything that would make cosine negative is invalid because r squared, it's not going to be able to equal to that. So just you have to kind of watch out for your domains here. So the question is, okay, how do I graph this thing? Now, here's the trick on graphing polar equations that we haven't gone over yet. And you really just have to kind of make a table, but it's going to seem weird. I promise. It's going to be a little weird. So let's bring this out a little bit. So what we want to do is let's take theta all the way in places that it makes sense to go. Now remember, we can't have negative values. Now cosine is only positive from negative pi over 2 to pi over 2. So, cosine theta is greater than or equal to 0 if negative pi over 2 theta to pi over 2. But we actually have cosine of 2 theta. So cosine of 2 theta is only positive if we do that. If we go from negative pi to pi, negative pi to pi. Now, that's weird. I apologize. Hold on. That can't be true. That's actually, no, that's definitely false. You can't just double that because, I mean, you're going to end up with something like real dumb there. Like if I plug in pi over 3 for theta, I'm going to end up with cosine 2 pi over 3. That can't possibly be correct. So we're really just going to have to watch out. We're really just going to have to watch out that we don't cross over here. So I'm going to pick thetas all the way down to negative pi over 4, and then I'm going to come up to positive pi over 4, and then we'll deal with that. So When theta is negative pi over 4, that becomes cosine of negative pi over 2, which is 0. So then I get 0. Now, when theta is like negative pi over 3, or sorry, negative pi over 8, something like that, I get negative pi over 8. Well, then that's going to be plus or minus the square root of 3 square root of 3, square root of 2. If it's negative pi over 12, it's going to be plus or minus 3 square root of 3. That's kind of nasty, right? I know, I get it too. When theta goes up to 0, cosine of 0 is 1, so this is plus or minus square root of 6. Okay, and then we're going to do the same thing for positive values. We're going to get, pi over 12, pi over 8, and pi over 4. Well, cosine's an even function, so plugging in negative values and positive values get the same kind of outputs. So we're still going to get the same sort of outputs here. We're going to get negative plus or minus 3 square root of 3, or plus or minus 3 square root of 2, and then 0. So what does that mean? Now I've written all these values. What does this mean? Well, it's going to be fun. So at pi over 4 and negative pi over 4, r is 0. So along these lines, you actually have nothing there. Now, as you go to negative pi over 8, so along this line, you have a positive 3, or you have a positive 3 square root of 2, like square root of 3 square root of 2, so you have this. And you also have the negative case, you also have this. And then, as you get to negative pi over 12, it's even further out. And then when you get to 0, the radius is either square root of 6 or negative square root of 6. And then as you go up some more, you get, since these are reflections of each other, these are reflections of each other. So these will be reflections of each other. So what you're going to get is you're going to get something that's 0 here, then comes up, out, up, and back to 0, right? Because at negative pi over 4, you're at 0. And at negative pi over 4, you're 0. At positive pi over 4, you're 0. So it's going to kind of come up and out. Same thing's happening over here. It's going to be up and out. So you end up with this actually infinity style symbol. You end up with something that looks like this. This is called a lemniscate. This is one of the standard polar graphs that happens. Again, this is kind of difficult to envision. I mean, well, especially if I'm in front of it. This is kind of difficult to envision. You have to kind of plot and follow that trajectory. That's one of the reasons that doing that, what's it called? It's not the trajectory, but the orientation. One of the reasons that orientation is helpful is that you can kind of fill in the gaps yourself if you know how the orientation goes. You can kind of see how that's rocking back and forth. And so the lemniscate can be drawn from that sort of thing. Trying to do that in rectangular would be a nightmare. Just imagine trying to plug in an x value and solving for y here. It'd be pretty ugly. I mean, obviously when x is 0, it's not too bad. But when x is, 1, ugh, good luck, right? It's nasty. So you wouldn't really want to do that. The polar equation actually makes more sense. You can plug in points, kind of fill in your picture, and get a better feeling for it. So again, try some of this stuff on your own, see if you can get it. But ultimately, this stuff is kind of nasty, so you're going to need a decent amount of practice.